Today we're going to look at limits and continuity, parts E and F. I'm going to skip D and I'm going to combine what was E and F into one lesson here. Continuity refers to the connectedness of the function. That means a function is continuous if there are no breaks or holes in it. So y equals x squared is continuous everywhere, while x squared divided by x plus 1 is not continuous at x equals -1 because there's a hole in the graph there. Because mathematicians like to get carried away, this simple idea has a sophisticated sounding three-part proof to verify continuity. In other words, a function is continuous because it looks that way. The three-part test for continuity at a point, okay, this test doesn't prove a function is continuous everywhere, only shows that it's continuous at a particular point. So to prove a continuity at point x equals a, show that the function exists at that point, f of a exists. If it doesn't exist, well, then the function isn't continuous there because there is no value. Show that the limit as x approaches a of f of x exists. If there is no limit, then the function is not continuous. And finally, show that f of a is equal to that limit of f of x as x approaches a. If these do not match, the function is not continuous. So let's take a look at the above test in more English-sounding words. 1, does the point exist? Does the graph exist near that point? And do the point and the graph match up? If the function passes all three parts of the test, then it is continuous. So let's take a look at an example. Is f of x equals x squared minus 3 continuous at x equals 0? Well, f of 0 equals -3, so that was good. 2, the limit of f of x as x approaches 0 is also equal to -3. So that works. And those two are equal to each other. So part 3 works. So yes, it is continuous at x equals 0. Let's look at an example. Is f of x equals, now the stepwise function, x plus 2, if x is less than -1, x minus 3 at x greater than or equal to -1, well, is it continuous at x equals -1? Well, f of -1 would fall into the second function here. So -1 minus 3 is equal to -4. So the point exists there. Now, let's look at number 2, though. Since it's a piecewise function, we must use left and right-hand limits. So coming from the left, we're going to take the first equation because it's up to but not including -1. So at -1, the limit is going to be -1 plus 2 is equal to +1. Now the function doesn't equal +1, but the limit does there. Coming from the right side, f of x equals x minus 3. Well, at -1, that's going to approach -4, just like we did in part 1. But since these two do not equal each other, the limit does not exist, and the function is not continuous at x equals -1. And you could probably graph that and visualize it, but this is how we would do it mathematically. And since number 2 failed, we don't have to do step 3. All right. Now, mathematicians like to classify continuities in with three different terms. Removable discontinuities, infinite discontinuities, and jump discontinuities. And we'll take a look at what each one of these means. So first we'll look at removable discontinuities. Graphically, these would be tiny holes in the graph. The limit exists, but the function has a break. For example, x squared divided by x is not defined at x equals 0. There would be a hole in the graph there. At every other point in the domain, there would be a value, but at x equals 0, there would be a hole. So that's what we call a removable removable discontinuity. Okay, so algebraically, these occur when the function gives 0 over 0, but you can still evaluate the limit by factoring. So, for example, f of x equals x minus 1, okay, divided by x squared minus 1. Well, look what happens at x equals 1. F of 1 is 0 over 0, so the function doesn't exist. But after factoring, we can factor this into x squared, x minus 1 times x plus 1, and the x minus 1's cancel out, and we're left with 1 over x plus 1. So the limit as x approaches 1 of f of x is 1/2. But the function doesn't exist there. So since the function doesn't exist there, but the limit does, well, that's what we call a removable discontinuity at x equals 1. Infinite discontinuities. This was when we deal with um, infinite limits. Graphically, these occur at vertical asymptotes. So what would that look like? Algebraically, these occur when the function gives a number over 0. So the limit's going to look like infinity. So look what happens at this function, x minus 1 over x plus 1, at x equals negative 1. At x equals negative 1, the function is negative 2 over 0. So the function doesn't exist there. So therefore, this function has an infinite discontinuity at negative 1, which means the limit of this is going to be infinite. Finally, just jump discontinuities, as you might have guessed, is, well, where there's a jump in the graph. Algebraically, these tend to happen with piecewise functions, step functions, and it can happen also with absolute value functions. Take a look. So example, f of x equals the greatest integer in x. Remember that double bracket means greatest integer, also called a step function. This function has a discontinuity at every integer because remember anything between 0 and 1 goes back to the greatest integer 0. Between 1 all the way up to, but not including 2, goes back to 1. So it's a step function. So there are breaks at every, or jumps at every integer. What about a piecewise function like this? X squared minus 1 at x less than or equal to 2, or x plus 2 at x greater than 2. Well, this has a jump discontinuity at x equals 2. At x equals 2, well, the function is going to be 2 squared minus 1 is equal to 3. Okay, so the function is 3. But the limit here is, for the first equation, the left-hand limit is going to be 3, but the right-hand limit, as we approach from the right-hand side, is going to be 4. So it has two different limits at at x equals 2. The function is going to be 3, but the left-hand limit is 3, the right-hand limit is 4. Therefore, it's a jump discontinuity. Now, don't assume that all piecewise functions have jump discontinuities. We have to test them because they might just happen to match up right at that point, in which case there is no discontinuity. Now, we can also have a jump discontinuity in an absolute value function. Here we have the absolute value of x minus 2 all over x minus 2. Well, this is going to be equal to negative 1 for all values less than 2. This is going to be equal to positive 1 for all values greater than 2. But at 2, there's a jump because it jumps from negative 1 up to positive 1 at 2. Now, you might want to try graphing some of these on your calculator to visualize this, because that will help you visualize it. Locating discontinuities. Removable and infinite discontinuities are easy to locate. Simply set the denominator of your fraction equal to 0. Jump discontinuities are a little more difficult. Okay? So Step functions, we know that the jump discontinuities occur at every step. Piecewise function, discontinuities may occur at each transition value, not necessarily. They might match up, but if they don't, then that's a jump discontinuity. And absolute value, wherever the absolute value part equals 0, we might have a jump discontinuity there as well. So you got to check that too. All right, at this point, we're going to switch over to the in-class worksheet and take a look at that.